What Webb saw 625 light-years away has left scientists stunned. A swirling disk of chaos, creating moons in a place where no moon should ever form. Something that's never been observed before in the history of astronomy. A cosmic factory where moons are being born right before our very eyes. Tonight we're diving into a discovery so profound it's rewriting our understanding of how moons form throughout the universe. The James Webb Space Telescope has just captured something remarkable. A carbon-rich disk of material swirling around a distant world, actively creating the building blocks for new moons. It's like peering into a cosmic nursery and watching the birth of celestial bodies that could one day harbour worlds as fascinating as our own. I'd love to know where you're listening from tonight. Feel free to comment your time and location below. If you find comfort in these gentle explorations of the universe, I'd be grateful if you'd consider subscribing and liking this video. It helps the algorithm find more curious souls like us who have an amazing passion for understanding our place in the cosmos. Your support helps me continue creating these deep dives into the mysteries that surround us. Picture this moment. You're standing in your backyard on a clear night, gazing up at the moon. That familiar silver disk has been Earth's companion for over 4 billion years, lighting our nights and stirring our oceans with its gravitational embrace. But have you ever wondered how our moon came to be? How any moon forms in the vast expanse of space? Tonight, thanks to an incredible discovery by the James Webb Space Telescope, we're about to find out. Deep in the constellation Chameleon, 625 light-years from Earth, something extraordinary is happening. A massive world called CT-B is surrounded by a swirling disk of material that's actively forming moons. For the first time in human history, we're not just theorizing about how moons form. We're watching it happen in real time, observing the cosmic processes that shaped our own lunar companion billions of years ago. This isn't just another distant exoplanet discovery. This is a window into the past, a cosmic time machine that shows us exactly how the moons in our own solar system might have formed when the universe was young. The implications are staggering. Not only does this discovery help us understand our own cosmic neighborhood, but it reveals that moon formation might be far more common and diverse than we ever imagined. CT-B exists in a realm that challenges our understanding of planetary classification. With a mass 17 times that of Jupiter, it sits on the boundary between what we call a planet and a brown dwarf, those mysterious objects that astronomers sometimes refer to as failed stars. But whether it's a massive planet or a small brown dwarf, doesn't diminish the significance of what's happening around it. This cosmic giant is orbiting its young star at an incredible distance of 440 astronomical units. That's roughly 46 billion miles away from its host star, a separation so vast that it creates the perfect conditions for something remarkable to occur. The story begins in the Chameleon Y star-forming region, one of the nearest active stellar nurseries to Earth. This cosmic maternity ward is filled with young stars, most barely 2 million years old, still in the process of gathering material from their surroundings. It's a region where the universe is actively creating new worlds, new systems, new possibilities for life as we know it. Among these stellar infants lies CT-B's host star, itself just 2 million years old, and still hungrily accreting material from the cosmic environment around it. What makes this system truly special is the unprecedented view it provides into moon formation. For decades, astronomers have theorized about how large moons like Jupiter's Galilean satellites formed. The leading theory suggested they condensed from disks of material that surrounded their parent planets during formation, much like how planets form from disks around stars. The evidence for this theory was compelling but indirect. The coplanar orbits of Jupiter's major moons, all circling in nearly the same plane, suggested they formed from a flattened disk rather than being captured asteroids. The mixed ice and rock composition of the outer Galilean moons further supported this disk formation model. But theory is one thing, and direct observation is another entirely. Until now, no one had ever actually seen a moon-forming disk around another planet. We could infer their existence, model their properties, and predict their behavior, but we couldn't observe them directly. That changed when astronomers turned Webb's incredible infrared vision toward CT-CHAR-B and discovered something that would revolutionize our understanding of moon formation. The technical achievement of this observation cannot be overstated. Imagine trying to study a firefly dancing next to a searchlight from hundreds of miles away. That's essentially what astronomers had to do to isolate the faint infrared glow of CT-CHAR-B's moon-forming disk from the brilliant light of its host star. The planet's signal was buried in the overwhelming glare of stellar radiation, requiring sophisticated high-contrast imaging techniques and an entire year of painstaking data analysis. The process began when researchers noticed something intriguing in Webb's archival data. There were molecular signatures detected at the planet's location, faint fingerprints of chemistry that hinted at something extraordinary happening in that distant system. What followed was a year-long analytical marathon, with scientists developing new methods to tease apart the various sources of infrared light and isolate the specific emission coming from the circumplanetary disk. When the analysis was complete, the results were nothing short of revolutionary. Webb had not only detected the disk, but had also measured its chemical composition in unprecedented detail. The telescope revealed a rich inventory of carbon-bearing molecules swirling around CT-CHAR-B, including acetylene, benzene, hydrogen cyanide, and several other complex organic compounds. These weren't just random molecules floating in space. They were the raw materials for moon formation, the cosmic ingredients that could condense and aggregate to form rocky worlds with complex chemical compositions. Perhaps the most intriguing discovery was the detection of benzene, a fundamental building block for polycyclic aromatic hydrocarbons. These complex organic molecules are found throughout the universe and represent some of the most sophisticated chemistry that occurs naturally in space. The presence of benzene in CT-CHAR-B's disk suggests that moons forming in this environment could develop organic-rich surfaces and potentially even subsurface oceans with intricate chemical processes. But here's where the story takes a fascinating turn. The chemical composition of the moon-forming disk around CT-CHAR-B is dramatically different from the planet-forming disk around the host star. While the circumplanetary disk is rich in carbon molecules, the stellar disk contains water, but virtually no carbon compounds. This chemical dichotomy reveals something profound about how planetary systems evolve and differentiate during their formation. The contrast suggests that different regions of the same planetary system can develop entirely distinct chemical signatures, even over relatively short timescales. The CT-CHAR system is only 2 million years old, yet it has already evolved complex chemical gradients that will determine what types of worlds form in different regions. This chemical separation occurs through various processes, including temperature gradients, dust migration, photochemical reactions driven by stellar radiation, and the gravitational influence of forming planets. Understanding this chemical differentiation is crucial for predicting what types of planets and moons might form throughout the galaxy. If circumplanetary disks commonly develop carbon-rich chemistry, while their parent stellar disks remain water-rich, it suggests that exomoons could exhibit far greater compositional diversity than objects in our own solar system. We might expect to find moons with organic-rich surfaces, complex atmospheric chemistry, and perhaps even the ingredients necessary for prebiotic processes under the right conditions. The formation process itself occurs through multiple stages of accretion and gravitational assembly that unfold over millions of years. It begins with tiny dust grains and ice particles that stick together through electrostatic forces and van der Waals interactions. These microscopic building blocks gradually coalesce into larger aggregates, then planetesimals ranging from centimeters to kilometers in size. As these objects continue to collide and merge, they form progressively larger bodies that eventually become moon-sized worlds. The dynamics of this process are incredibly complex, involving gravitational interactions between forming moons and the disk material, resonances that can either promote or inhibit moon formation, and tidal forces from the parent planet that shape orbital characteristics. The specific properties of each circumplanetary disk, including its mass, radial extent, and material distribution, all influence the final outcome. Different conditions can lead to single large moons, multiple smaller satellites, or intricate moon systems with complex orbital relationships. What makes CT-CHARB's disk particularly fascinating is its location within what astronomers call the dead zone of the circumplanetary environment. This region is characterized by low turbulence and reduced mixing, creating ideal conditions for solid particles to settle and aggregate efficiently. It's in these quiet zones that moon formation is most likely to succeed, allowing dust and ice to accumulate into increasingly larger bodies without being disrupted by violent disk dynamics. The discovery also provides crucial insights into the prevalence of moons throughout the galaxy. As astronomers continue to discover thousands of exoplanets orbiting distant stars, it's becoming clear that moons may vastly outnumber planets in the universe. Some of these exomoons could be large enough to maintain atmospheres, support active geology, and perhaps even harbor conditions suitable for life as we know it. This possibility transforms our perspective on where life might exist in the cosmos. While much attention has focused on potentially habitable exoplanets, the universe's most common habitable worlds might actually be moons. The discovery of carbon-rich chemistry in CT-CHARB's disk suggests that some of these moons could develop the complex organic chemistry necessary for life, expanding our conception of cosmic habitability far beyond traditional planetary systems. The implications extend to understanding our own solar system's history as well. The moons of Jupiter and Saturn exhibit remarkable diversity in composition and structure, from the volcanic activity of Io to the subsurface oceans of Europa and Enceladus. By studying how moons form in systems like CT-CHARB, we gain insights into the processes that created this diversity and shape the evolution of our cosmic neighborhood over billions of years. The Webb telescope's ability to peer into this distant moon factory represents a technological marvel that pushes the boundaries of what we thought possible in astronomical observation. When you consider that the infrared light we're analyzing left CT-CHARB's system over 600 years ago, during the height of the Ming dynasty here on Earth, you begin to appreciate the profound nature of this cosmic archaeology. We're not just observing distant chemistry, we're witnessing the fundamental processes that govern how worlds come into being across the universe. The sophistication required to isolate these molecular signatures from the overwhelming stellar glare cannot be understated. Picture trying to identify the chemical composition of a candle flame while someone shines a stadium floodlight directly into your eyes from the same direction. That's essentially the observational challenge that Webb's instruments had to overcome. The telescope's mid-infrared instrument, or MIRI, operated at the very limits of its sensitivity to capture the thermal glow of dust and gas in this remote circumplanetary disk. The year-long analysis that followed the initial detection reads like a detective story of cosmic proportions. Astronomers had to develop entirely new techniques for extracting planetary signals from stellar contamination, creating algorithms that could distinguish between different sources of infrared emission across multiple wavelengths. Each molecule in the disk has its own unique spectral fingerprint, a pattern of absorption and emission lines that serves as its cosmic signature. By carefully analyzing thousands of these spectral features, the research team built up a complete chemical inventory of the moon-forming environment. What emerges from this painstaking analysis is a picture of extraordinary chemical complexity. The circumplanetary disk around CT B contains not just simple molecules, but sophisticated organic compounds that hint at the rich chemistry possible in these distant worlds. Acetylene, detected in abundance throughout the disk, can undergo cyclotrimerization reactions to form benzene rings under the right conditions. These benzene molecules then serve as building blocks for even more complex polycyclic aromatic hydrocarbons, creating a cascade of organic chemistry that could rival the complexity found in Earth's early atmospheric evolution. The presence of hydrogen cyanide adds another layer of astrobiological intrigue to this cosmic chemistry set. Under certain conditions, hydrogen cyanide can polymerize to form adenine, one of the fundamental nucleotide bases found in DNA and RNA. While we're certainly not suggesting that life could emerge in the harsh environment around CT the detection of these prebiotic molecules demonstrates that the universe has a remarkable capacity for creating the chemical ingredients associated with biological processes. Perhaps most fascinating is how this chemical inventory compares to what we observe in meteorites and comets from our own solar system. Many of the organic compounds detected in CT disk have also been found in carbonaceous chondrites, those primitive meteorites that preserve samples of the early solar nebula. This suggests that the organic chemistry we're witnessing around this distant world may be representative of processes that occurred throughout our own cosmic neighborhood billions of years ago. The stark chemical contrast between the circumplanetary and circumstellar disks tells a story of rapid evolution and differentiation. Within just 2 million years, these two regions of the same planetary system have developed completely different chemical personalities. The stellar disk, rich in water ice but depleted in carbon compounds, represents one evolutionary pathway. The planetary disk, dominated by carbon chemistry but apparently lacking significant water content, represents another entirely different trajectory. This chemical segregation likely results from a combination of physical processes operating on different timescales throughout the system. Temperature gradients established by stellar radiation create zones where different molecules can condense from the gas phase. Dust grains migrate through the disk under various dynamical influences, carrying their chemical cargo to different regions. Photochemical reactions triggered by high-energy stellar photons break down some molecules while promoting the formation of others. The gravitational influence of the massive planet itself may create pressure and density variations that favor certain chemical pathways over others. Understanding these differentiation mechanisms has profound implications for predicting the diversity of worlds that might exist throughout the galaxy. If circumplanetary disks routinely develop chemical compositions that differ dramatically from their parent stellar environments, then moons forming in these regions could exhibit properties unlike anything we see in our own solar system. We might expect carbon-rich moons with organic-dominated surfaces, complex atmospheric chemistry involving hydrocarbon hazes, and perhaps even subsurface environments where sophisticated organic reactions could occur over geological timescales. The discovery also illuminates the incredible efficiency with which nature can organize complex chemistry from relatively simple starting materials. The transition from basic molecules like acetylene and hydrogen cyanide to complex ring structures like benzene occurs through well-understood chemical pathways. But observing these processes operating in a natural cosmic environment provides crucial validation of our theoretical understanding. It demonstrates that the universe operates as a vast chemical laboratory, constantly experimenting with new combinations of atoms and molecules under conditions we can barely replicate on Earth. The implications for moon formation theory extend far beyond simple chemical inventory. The physical structure of circumplanetary disks, their temperature profiles, density distributions, and dynamical evolution all influence how and where moons can successfully form. The dead zone regions where turbulence is suppressed provide ideal conditions for solid particles to settle and begin the accretion process. The balance between inward migration of disk material and outward migration of forming moons determines which satellites survive to become permanent members of the planetary system. Computer simulations of these formation processes reveal an astonishing diversity of possible outcomes. Some circumplanetary disks produce single large moons comparable to our own moon. Others generate complex systems of multiple satellites with intricate orbital relationships. Still others create temporary moon populations that eventually spiral into their parent planets or are ejected into interplanetary space. The specific evolutionary pathway depends on countless variables, including disk mass, planet rotation rate, stellar environment, and the precise timing of various dynamical processes. The CT-CHAR-B system provides our first opportunity to observe these theoretical processes in action. Rather than relying solely on computer models and laboratory experiments, we can now study real circumplanetary chemistry and dynamics in a natural cosmic environment. This observational foundation will undoubtedly lead to refinements in our theoretical understanding and perhaps reveal entirely new aspects of moon formation that we haven't yet considered. The success of these observations also opens the door to studying similar systems throughout our galactic neighborhood. Webb's extraordinary sensitivity means that circumplanetary disks around other young planets are now accessible to detailed spectroscopic analysis. Each new system we observe will add another piece to the puzzle of moon formation, gradually building up a comprehensive picture of how satellite systems evolve under different conditions throughout the universe. As we continue to push the boundaries of what's observable with current technology, we're entering an era where the formation of entire planetary systems can be studied in exquisite detail. The birth of planets, the emergence of moons, the chemical evolution of circumstellar environments, and the development of the complex architectures we see in mature planetary systems can all be observed directly rather than simply inferred from theoretical models. This observational revolution promises to transform our understanding of how common moon-bearing planets might be throughout the galaxy. If circumplanetary disks are a natural consequence of giant planet formation, and if these disks routinely produce substantial satellite systems, then the universe may be filled with moon-bearing worlds that dwarf the satellite populations in our own solar system. Some of these exomoons could be massive enough to maintain thick atmospheres, active geology, and perhaps even magnetic fields generated by internal dynamo processes. The chemical diversity revealed by CT-CHAR-B suggests that these distant moons could exhibit properties that stretch our imagination. Carbon-rich worlds with organic snow, methane lakes, and hydrocarbon atmospheres. Ice-rich satellites with subsurface oceans containing dissolved organic compounds. Rocky moons with mineral compositions unlike anything found in our solar system. The possibilities seem virtually limitless, constrained only by the fundamental laws of chemistry. and physics. Tonight, as you drift towards sleep under the gentle glow of our own moon, consider that you're witnessing a cosmic moment of unprecedented discovery. We're living during the first generation of humans who can directly observe moon formation occurring around distant worlds, who can analyze the chemistry of cosmic environments separated from us by hundreds of light years, who can begin to appreciate the true diversity and complexity of planetary systems throughout our galaxy. The story of CT-CHAR-B is still unfolding, with new observations and analysis continuing to reveal additional layers of complexity and beauty in this distant moon factory. Each spectral line decoded, each molecular signature identified, each physical process understood, brings us closer to comprehending our own cosmic origins and our place in the vast tapestry of worlds that populate the universe. This discovery fundamentally challenges our assumptions about the timescales involved in planetary system evolution. When we consider that chemical differentiation between the stellar and planetary disks occurred in just 2 million years, we're witnessing processes that operate with remarkable speed on cosmic scales. 2 million years might seem like an eternity from our human perspective, but in astronomical terms, it's barely a moment. Stars like our Sun will shine for billions of years, yet the fundamental chemistry that determines what types of worlds can form is established in less than 1% of a stellar lifetime. The rapid evolution observed in the CT-CHAR system suggests that the window for moon formation may be surprisingly brief. Circumplanetary disks don't persist indefinitely. As the parent planet continues to grow and evolve, as stellar winds strip away disk material, and as forming moons gravitationally clear their orbital paths, these cosmic nurseries gradually dissipate. The moons that successfully form during this critical period will become permanent members of their planetary system, while the raw materials that fail to coalesce are lost to space or absorbed by the central planet. This temporal constraint adds urgency to the moon formation process and helps explain why some planetary systems end up with rich satellite populations while others remain relatively barren. The specific timing of disk formation, the rate of material inflow, and the efficiency of accretion processes all contribute to determining the final outcome. In systems where these factors align favorably, we might expect to find elaborate moon systems with dozens or even hundreds of satellites. In less favorable environments, planets may acquire only a few small moons, or none at all. The chemical complexity revealed in CT-CHAR-B's disk also raises intriguing questions about the role of organic chemistry in early planetary system evolution. The detection of sophisticated carbon compounds suggests that organic synthesis occurs naturally in circumplanetary environments, creating reservoirs of complex molecules that could influence the subsequent evolution of any worlds that form in these regions. These organic inventories might persist in moon interiors for billions of years, potentially providing chemical energy sources or catalytic surfaces that could drive unexpected geological processes. Consider the implications for subsurface chemistry on carbon-rich moons. If substantial quantities of organic compounds become incorporated into moon interiors during formation, they could create reducing environments that persist long after the original circumplanetary disk has dissipated. Interactions between organic molecules and mineral surfaces could generate chemical gradients, electron donors and acceptors, and perhaps even primitive metabolic networks that operate independently of stellar energy input. While such processes wouldn't constitute life as we understand it, they could create the chemical foundations upon which biological systems might eventually build. The diversity of molecular species detected around CT-CHAR-B also demonstrates the sophisticated chemical processing that occurs within circumplanetary disks. These environments aren't simply passive repositories of dust and gas, but active chemical reactors where molecules are constantly being created, modified, and destroyed through various physical and chemical processes. Ultraviolet radiation from the central star drives photochemical reactions that break molecular bonds and create reactive fragments. Shock waves propagating through the disk can trigger high-temperature chemistry that wouldn't occur under equilibrium conditions. Grain surface catalysis allows complex molecules to form through pathways that would be impossible in the gas phase alone. This chemical dynamism means that the molecular inventory of a circumplanetary disk is constantly evolving throughout the moon formation process. Early in disk evolution, simple molecules like water, carbon monoxide, and molecular hydrogen dominate the composition. As time progresses and various chemical pathways become active, more complex species begin to appear. The detection of molecules like benzene and hydrogen cyanide in CT-CHARB's disk suggests that we're observing a relatively mature phase of chemical evolution, where sophisticated organic synthesis has had time to produce substantial quantities of complex compounds. The spatial distribution of these molecules within the disk adds another layer of complexity to the moon formation process. Different chemical species will condense from the gas phase at different temperatures and pressures, creating chemical gradients throughout the circumplanetary environment. Water ice might dominate the outer regions where temperatures are low, while refractory organic compounds could be concentrated in warmer inner zones. This chemical stratification means that moons forming at different distances from their parent planet could acquire dramatically different compositions, even if they originate from the same disk. Such compositional gradients could lead to moon systems with remarkable diversity. Inner moons might be carbon-rich worlds with organic-dominated surfaces and reducing atmospheres rich in hydrocarbons. Middle-distance satellites could represent transitional compositions with mixed ice-rock organic inventories. Outer moons might be primarily water ice with relatively simple chemistry. The specific boundaries between these compositional zones would depend on the temperature structure of the disk, which itself is determined by heating from the central planet, stellar irradiation, and internal viscous dissipation. The long-term evolution of such chemically diverse moon systems opens up fascinating possibilities for comparative planetology. As these satellites evolve over billions of years, their different starting compositions could lead to dramatically different evolutionary pathways. Carbon-rich moons might develop thick organic hazes in their atmospheres, similar to what we observe on Saturn's moon Titan, but potentially much more complex. Ice-rich satellites could maintain subsurface oceans for geological ages, creating stable environments where chemical evolution could proceed along pathways impossible on planet surfaces. The gravitational interactions between multiple moons in such systems could further complicate their evolution. Orbital resonances might pump energy into satellite interiors through tidal heating, driving volcanism, tectonism, and perhaps even the differentiation of organic compounds into distinct chemical layers. Some moons might exchange material through impact processes, creating hybrid compositions that combine the chemical inventories of multiple worlds. Others might capture debris from disk material or collisional fragments, gradually accreting additional chemical complexity over time. The study of CT-CHARB's circumplanetary disk also provides crucial calibration for theoretical models of moon formation that have been developed over decades of research. Computer simulations of these processes require detailed input parameters describing disk properties, chemical compositions, temperature profiles, and dynamical evolution. Until now, many of these parameters had to be estimated or extrapolated from indirect observations. The Webb data provides the first direct measurements of circumplanetary disk chemistry, allowing theorists to test their models against real observations and refine their predictions accordingly. Initial comparisons between the observed chemical inventory and theoretical expectations reveal both confirmations and surprises. The detection of complex organic molecules validates predictions that sophisticated chemistry should occur in circumplanetary environments. However, the specific molecular species detected, their relative abundances, and their spatial distribution don't perfectly match any existing theoretical model. This discrepancy highlights the complexity of real circumplanetary environments and suggests that our theoretical understanding still has room for improvement. The temperature structure inferred from the molecular observations also provides important constraints on disk physics. Different molecules have different thermal stability limits, so their presence or absence can be used to map temperature variations throughout the circumplanetary environment. The survival of complex organic compounds like benzene suggests that at least some regions of the disk maintain relatively moderate temperatures, where these molecules can exist in stable form. This temperature mapping is crucial for understanding where different types of moons are most likely to form and what compositions they might acquire. The discovery also has profound implications for understanding the formation of our own solar system's satellites. Jupiter's Galilean moons have long been recognized as a miniature planetary system in their own right, with regular orbital spacings, systematic compositional trends, and clear evidence for formation from a circumplanetary disk. The detection of complex organic chemistry around CT-CHAR-b suggests that Jupiter's circumplanetary disk might also have contained sophisticated molecular inventories during the formation of its satellite system. This possibility could help explain some puzzling aspects of Galilean moon compositions that have challenged planetary scientists for decades. The presence of organic compounds in Europa's subsurface ocean, the complex surface chemistry observed on Ganymede and Callisto, and the unusual isotopic signatures found in meteorites thought to originate from the outer solar system might all be traces of primordial, circumplanetary chemistry that occurred during Jupiter's formation 4.5 billion years ago. The systematic compositional gradient observed among the Galilean satellites, with ice-poor Io closest to Jupiter and ice-rich Callisto farthest away, could reflect the temperature structure and chemical gradients that existed in Jupiter's primordial circumplanetary disk. If that disk contained complex organic molecules similar to those detected around CT-CHAR-b, then substantial quantities of these compounds might have been incorporated into the forming satellites, particularly the outer moons, where temperatures were low enough for organic species to condense and survive. Similarly, Saturn's moon system might preserve evidence of complex circumplanetary chemistry from the early solar system. Titan's thick atmosphere and surface lakes of liquid hydrocarbons could represent the end result of billions of years of evolution, starting from organic-rich materials incorporated during moon formation. The organic chemistry observed on Titan today might be a direct descendant of primordial circumplanetary processes that occurred when Saturn was still surrounded by its moon-forming disk. The Webb observations of CT-CHAR-b provide a tantalizing glimpse into what Saturn's circumplanetary environment might have looked like during Titan's formation. The detection of acetylene, benzene, and other hydrocarbon species suggests that similar molecules were likely present around the young Saturn, potentially providing the chemical foundation for Titan's current atmospheric and surface chemistry. Understanding these connections between primordial disk chemistry and present-day satellite properties could revolutionize our understanding of how moon systems evolve over geological time. The discovery also raises intriguing questions about the potential for detecting similar circumplanetary disks around planets in our own solar system. While the major planets completed their formation billions of years ago and no longer maintain substantial circumplanetary disks, there might be transient disk formation events associated with major impact processes. When large asteroids or comets collide with planets or their existing moons, they can create debris disks that temporarily surround the parent world. These impact-generated disks could potentially undergo chemical evolution, similar to what we observe around CT-CHAR-B, albeit on much shorter timescales and smaller scales. The complex organic chemistry that might develop in such environments could influence the composition of any small satellites that accrete from the debris. Recent theoretical work suggests that Earth's moon itself might have formed from such an impact-generated circumplanetary disk, raising the possibility that our own satellite incorporated complex organic compounds during its formation. The implications extend beyond our solar system to the broader question of how common moon-bearing planets might be throughout the galaxy. If circumplanetary disk formation is a natural consequence of giant planet formation, and if these disks routinely produce substantial satellite systems, then the universe could be populated with countless moon-bearing worlds. Each of these systems might exhibit the kind of chemical complexity and diversity revealed by the CT-CHAR-B observations, creating a cosmic menagerie of satellite systems with properties that stretch our imagination. The chemical diversity suggested by these observations has profound implications for astrobiology and the search for life beyond Earth. While planets have traditionally been the focus of habitability studies, moons might actually represent the most common, potentially habitable worlds in the universe. The complex organic chemistry observed in circumplanetary environments suggests that many of these moons could acquire the chemical ingredients necessary for life during their formation, providing a head start on the long process of biological evolution. The subsurface oceans that likely exist on many large moons could serve as protected environments where complex chemistry can proceed over billions of years without interference surfaced from the primordial circumplanetary disk. They might support conditions. If these oceans contain dissolved organic compounds, inherit chemical networks of remarkable sophistication. While we can't yet determine whether such environments could actually give rise to living systems, the chemical foundations appear to be far more widespread and diverse than previously imagined. As we continue to analyze the wealth of data from CT-CHAR-B and search for similar systems throughout our galactic neighborhood, we're entering an era where the formation and evolution of entire planetary systems can be studied in unprecedented detail. Each new circumplanetary disk we discover will add another piece to the puzzle of moon formation, gradually building up a comprehensive picture of how satellite systems develop under different conditions throughout the universe. The story of CT-CHAR-B represents just the beginning of this observational revolution. Webb's extraordinary capabilities mean that dozens or perhaps hundreds of similar systems are now accessible to detailed study. Each one will reveal new aspects of circumplanetary chemistry and physics, expanding our understanding of the processes that govern moon formation and evolution. Some systems might show chemical inventories dominated by water and simple compounds, while others could exhibit even more complex organic chemistry than what we see around CT-CHAR-B. The diversity of circumplanetary environments we're beginning to uncover suggests that moon systems throughout the galaxy might exhibit a staggering range of properties and evolutionary pathways. We're only just starting to appreciate the true scope and complexity of these distant worlds, but already it's clear that the universe's capacity for creating diverse and fascinating satellite systems far exceeds anything we might have imagined based solely on our own solar system's examples. Tonight, as you settle into the gentle rhythm of approaching sleep, consider that we're living through a transformative moment in human understanding of the cosmos. We're the first generation to directly observe moon formation occurring around distant worlds, to analyze the chemistry of environments separated from us by hundreds of light years, to begin comprehending the incredible diversity of planetary systems that populate our galaxy. The cosmic story we're uncovering is far richer and more complex than our ancestors could have dreamed, filled with worlds and processes that challenge our imagination and expand our conception of what's possible in this vast universe we call home. The technical marvel of Webb's achievement becomes even more profound when we consider the sheer scale of what we're witnessing. The light we're analyzing left the CT-CHAR system during the late medieval period here on Earth, carrying within its infrared wavelengths the chemical signatures of a world in the process of creating its own family of satellites. Every photon that Webb captured had been traveling through the cosmic void for over 6 centuries, preserving within its energy the story of molecular processes occurring in an environment so distant and alien that it challenges our ability to truly comprehend its reality. Yet here we are, using instruments of extraordinary sophistication to decode these ancient messages and reconstruct the chemistry of a circumplanetary disk that exists in a realm beyond our direct experience. The mid-infrared instrument aboard Webb operates at temperatures colder than the depths of space. Its detectors cool to just a few degrees, above 0 degrees Celsius, absolute zero, to achieve the sensitivity necessary for these observations. When you consider that we're measuring thermal emission from dust grains and gas molecules that are themselves no warmer than a winter day on Earth, the technical achievement borders on the miraculous. The spectroscopic analysis that revealed CT-CHAR-B's chemical inventory reads like a cosmic detective story. Each molecule in the circumplanetary disk leaves its own unique fingerprint in the infrared spectrum, a pattern of absorption and emission lines that serves as an unmistakable signature of its presence and abundance. Benzene rings absorb infrared light at specific wavelengths determined by the vibrational modes of their carbon-hydrogen bonds. Acetylene molecules exhibit their own distinct spectral features based on the stretching and bending motions of their triple-bonded carbon atoms. Hydrogen cyanide reveals itself through the characteristic frequencies at which its molecular bonds oscillate when excited by thermal energy. By carefully measuring thousands of these spectral features across multiple infrared wavelengths, astronomers constructed a complete chemical census of the moon-forming environment. But this wasn't simply a matter of identifying which molecules were present. The intensity of each spectral line provides information about molecular abundances, while the precise wavelength shifts reveal the physical conditions under which these molecules exist. Temperature variations cause predictable changes in molecular emission patterns. Pressure effects alter the shapes and widths of spectral lines. Even the motion of gas within the disk creates Doppler shifts that can be measured and analyzed to understand the dynamics of this distant world. The year-long analysis required to extract these results pushed the boundaries of infrared spectroscopy and data processing techniques. Imagine trying to identify the ingredients in a recipe by analyzing the aroma from a kitchen located on the other side of the world, while someone simultaneously operates a massive bonfire right next to your detection equipment. That's essentially the observational challenge that confronted the research team. The overwhelming infrared emission from CT-CHAR-B's host star threatened to completely mask the much fainter signal from the circumplanetary disk, requiring innovative methods for separating these overlapping sources of radiation. The breakthrough came through the development of sophisticated algorithms that could model the expected stellar emission and subtract it from the total observed signal. This process, known as stellar subtraction, had to account for variations in stellar brightness, atmospheric effects that altered the infrared transmission, and instrumental artifacts that could mimic planetary signals. Only after removing all these contaminating effects could the true spectrum of the circumplanetary disk emerge from the data, revealing the molecular signatures that tell the story of moon formation in this distant system. What makes this achievement even more remarkable is that it represents the first successful application of these techniques to a circumplanetary environment. Previous observations had detected circumplanetary disks around young planets, but none had achieved the spectroscopic detail necessary to analyze their chemical composition. The success with CT-CHAR-B demonstrates that similar studies can now be conducted on other young planetary systems, opening an entirely new field of observational astronomy focused on understanding the chemistry and physics of moon formation throughout the galaxy. The implications of this technical breakthrough extend far beyond the CT-CHAR system itself. Webb's demonstrated ability to isolate and analyze circumplanetary disk emission means that astronomers can now systematically survey young planetary systems throughout our galactic neighborhood, building up a comprehensive database of moon-forming environments. Each new system studied will add to our understanding of how circumplanetary chemistry varies with different stellar environments, planetary masses, and evolutionary stages. Some systems might reveal circumplanetary disks dominated by water ice and simple carbon compounds, similar to what theoretical models predict for the early solar system. Others could exhibit even more exotic chemistry than what we see around CT-CHAR-B, perhaps containing sulfur-bearing molecules, silicon compounds, or organic species we haven't yet learned to recognize in astronomical spectra. The chemical diversity we're beginning to uncover suggests that the universe's capacity for creating complex molecular environments far exceeds anything we might have predicted based solely on laboratory experiments or theoretical calculations. The spatial resolution achieved in these observations also provides crucial insights into how chemical gradients develop within circumplanetary disks. While we cannot directly image the disk structure around CT-CHAR-B, the spectroscopic data contains subtle clues about where different molecules are concentrated within the circumplanetary environment. Molecules that require high temperatures to form will be more abundant in the inner regions close to the planet, while temperature-sensitive species will be concentrated in the cooler outer zones, where they can survive without being destroyed by thermal energy. This chemical stratification has profound implications for understanding what types of moons might form at different locations within the disk. Inner moons accreting in the warm, carbon-rich regions could acquire compositions dominated by refractory organic compounds and rocky materials. These worlds might develop into carbon-rich satellites with organic-dominated surfaces, reducing atmospheres rich in hydrocarbons, and perhaps even subsurface environments where complex organic chemistry could proceed over geological timescales. Middle-distance moons forming in transitional zones might acquire hybrid compositions, combining organic compounds with water ice and rocky materials. These satellites could represent some of the most chemically diverse worlds in the universe, with layered internal structures reflecting the varied materials available during their accretion. The interaction between organic compounds and water ice in such environments could drive chemical processes that we're only beginning to understand, potentially creating conditions that favor the formation of complex molecular networks. Outer moons accreting in the coldest regions of the circumplanetary disk might be dominated by water ice with smaller but still significant inventories of organic compounds. These worlds could maintain subsurface oceans for billions of years, providing stable liquid environments where the dissolved organic molecules inherited from the primordial disk could undergo continued chemical evolution. The combination of liquid water, organic compounds, and the energy sources provided by tidal heating could create conditions remarkably similar to what astrobiologists consider ideal for the emergence and evolution of life. The detection of hydrogen cyanide in CT-CHAR-B's disk adds a particularly intriguing dimension to these possibilities. Under appropriate conditions, hydrogen cyanide can polymerize to form adenine, one of the fundamental building blocks of DNA and RNA. While the harsh radiation environment and extreme conditions around CT-CHAR-B make it unlikely that such complex biochemistry could actually occur, the presence of hydrogen cyanide demonstrates that circumplanetary disks naturally produce molecules that are central to biological processes on Earth. This discovery raises fascinating questions about whether similar organic chemistry might have occurred in the circumplanetary disks that form the satellites of Jupiter and Saturn billions of years ago. If hydrogen cyanide and other prebiotic molecules were present during the formation of Europa, Enceladus, and other ice-rich moons, substantial quantities of these compounds might have been incorporated into their internal oceans. Over geological time, these primordial organic inventories could have evolved into complex chemical networks that persist to this day, hidden beneath kilometers of ice in environments we're only beginning to explore. The systematic compositional trends observed among different satellite systems in our solar system might reflect the chemical gradients that existed in their parent circumplanetary disks during formation. Jupiter's Galilean moons exhibit a clear pattern of decreasing density with increasing distance from the planet, suggesting that water ice became increasingly important in their compositions as distance from Jupiter increased. This trend could reflect the temperature structure of Jupiter's primordial circumplanetary disk, where refractory materials condensed in the inner regions, while volatile compounds like water remained in the gas phase until they reached cooler outer zones. The complex organic chemistry detected around CT-CHAR-B suggests that similar molecular diversity might have characterized the circumplanetary disks that formed our solar system's major satellite systems. If Jupiter's disk contained benzene, acetylene, and other hydrocarbon species during the formation of its moons, these compounds could have been incorporated into the satellites and subsequently evolved over billions of years of geological and chemical processing. Titan's current atmospheric and surface chemistry might represent the end result of this extended evolution, with the organic compounds we observe today being direct descendants of molecules that condensed from Saturn's primordial circumplanetary disk. The methane lakes, hydrocarbon precipitation, and complex atmospheric photochemistry that characterize Titan could all trace their origins to the organic inventory established during the Moon's formation over 4 billion years ago. The discovery also provides new insights into the timescales involved in moon formation and chemical evolution. The fact that CT-CHAR-B's circumplanetary disk has already developed such complex chemistry in just 2 million years demonstrates that these processes can occur with remarkable rapidity. From a cosmic perspective, 2 million years is barely a moment, yet it's apparently sufficient for sophisticated molecular synthesis to produce substantial inventories of complex organic compounds. This rapid chemical evolution suggests that the window for moon formation might be surprisingly brief, but intensely productive. Circumplanetary disks don't persist indefinitely. As planets continue to grow and evolve, stellar winds strip away disk material, and forming moons gravitationally clear their orbital paths. These cosmic nurseries gradually dissipate. The moons that successfully form during this critical period become permanent members of their planetary system, while unused materials are either absorbed by the central planet or dispersed into interplanetary space. The efficiency with which nature organizes complex chemistry from simple starting materials in these environments is truly remarkable. The transition from basic molecules like acetylene and carbon monoxide to sophisticated ring structures like benzene occurs through well-understood reaction pathways, but observing these processes in natural cosmic environments provides crucial validation of our theoretical understanding. It demonstrates that the universe operates as a vast chemical laboratory, constantly experimenting with new molecular combinations under conditions that span an enormous range of temperatures, pressures, and radiation environments. The success of the CT-CHAR-B observations also highlights the incredible potential for future discoveries as Webb continues its mission of cosmic exploration. The telescope's unprecedented infrared sensitivity means that circumplanetary disks around planets throughout our galactic neighborhood are now accessible to detailed spectroscopic analysis. Each new system we study will reveal different aspects of moon formation chemistry and physics, gradually building up a comprehensive picture of how satellite systems develop under various conditions throughout the universe. Some of these future observations might reveal circumplanetary disks with chemical inventories that make CT-CHAR-B's organic-rich environment seem simple by comparison. We might discover systems where sulfur chemistry dominates, creating exotic molecular species that don't exist anywhere in our solar system. Others might show evidence for silicon-based chemistry, metal-bearing compounds, or organic molecules of such complexity that they challenge our current understanding of interstellar chemistry. The diversity of stellar environments where these observations can be conducted also promises to reveal how different types of host stars influence circumplanetary chemistry. Young, massive stars produce intense ultraviolet radiation that could drive photochemical processes unlike anything that occurred during our solar system's formation. Lower mass stars, with different spectral characteristics, might create circumplanetary environments dominated by entirely different chemical pathways. Binary star systems could subject circumplanetary disks to complex gravitational and radiation environments that produce unique molecular inventories. As we continue to study these distant moon factories, we're developing an increasingly sophisticated understanding of how planetary system architecture influences satellite formation and evolution. The specific orbital configuration of planets within a system, their masses and compositions, the properties of their host stars, and the timing of various evolutionary processes all contribute to determining what types of moon systems ultimately develop. This growing database of circumplanetary observations will eventually throughout the galaxy. We'll be able to allow astronomers to make statistical statements about moon formation, what fraction of planets develop substantial satellite systems, how the properties of those systems depend on planetary and stellar characteristics, and whether the chemical complexity we observe around CT-CHAR-B is typical or exceptional among circumplanetary environments. The implications for astrobiology are particularly compelling. If complex organic chemistry proves to be common in circumplanetary disks throughout the galaxy, then the universe might be populated with countless moons that acquired sophisticated molecular inventories during their formation. These chemical foundations could provide the raw materials for continued evolution over billions of years, potentially leading to environments where life as we know it could emerge and thrive. The concept of habitable moons has gained increasing attention from astrobiologists in recent years, as it's become clear that satellites might actually outnumber planets as potentially life-bearing worlds. Large moons can maintain substantial atmospheres, support active geology through tidal heating, and provide stable environments that persist for geological ages. If these worlds also inherit complex organic chemistry from their formation environments, they might represent some of the most promising targets in our search for life beyond Earth. The chemical diversity revealed by circumplanetary disk observations suggests that any life that does emerge on these distant moons might be based on biochemistries quite different from what we see on Earth. Carbon-rich moons forming in environments like CT-CHAR-B's disk might support life forms that utilize the abundant hydrocarbon chemistry available on their surfaces. These organisms might derive energy from organic synthesis reactions, metabolize complex carbon compounds, or even incorporate aromatic ring structures into their biochemical machinery. Such possibilities stretch our imagination and challenge our Earth-centric assumptions about what life might look like elsewhere in the universe. The chemical foundations for alternative biochemistries appear to be naturally established during moon formation processes, suggesting that the universe might be far more creative in its approaches to organizing complex chemistry than we've previously recognized. The discovery also emphasizes the importance of studying circumplanetary environments as complete chemical ecosystems, rather than simply repositories of raw materials for moon formation. These disks are dynamic, evolving systems where molecules are constantly being created, modified, and destroyed through various physical and chemical processes. Understanding these evolutionary pathways is crucial for predicting what types of chemical legacies might be preserved in the moons that eventually form from disk material. The temporal evolution of circumplanetary chemistry also raises intriguing questions about whether we might be able to observe systems at different stages of moon formation and chemical development. CT-CHAR-B appears to represent a relatively mature phase of circumplanetary evolution, where sophisticated organic synthesis has had time to produce substantial inventories of complex molecules. Other systems might show us earlier stages of this process, where simpler chemistry dominates, but is beginning to evolve toward greater complexity. Observing this chemical evolution in action would provide unprecedented insights into how the molecular foundations of planetary systems develop over time. We might be able to trace the pathways by which simple starting materials gradually transform into the complex chemical inventories that ultimately determine what types of worlds can form in different cosmic environments. As our understanding of these processes continues to develop, we're also gaining new appreciation for the remarkable efficiency with which nature creates and organizes complex molecular systems. The chemistry we observe in circumplanetary disks emerges naturally from the interplay between fundamental physical processes and basic chemical principles, yet the results exhibit a sophistication that rivals anything we can create in terrestrial laboratories. This natural capacity for chemical self-organization has profound implications for understanding how complexity arises throughout the universe. If relatively simple physical systems can spontaneously develop intricate molecular inventories like those observed around CT-CHAR-B, then the transition from geochemistry to biochemistry might be more natural and probable than we've previously imagined. The ongoing analysis of Webb's circumplanetary disk observations continues to reveal new layers of complexity and beauty in these distant environments. Each molecular signature decoded, each chemical pathway identified, and each physical process understood brings us closer to comprehending the full scope of moon formation throughout the galaxy and our own cosmic origins within this vast community of worlds. Tonight, as the ancient light of distant stars touches your eyes and carries with it the stories of countless worlds beyond our reach, remember that we're living through an extraordinary moment in human history. We're the first generation capable of directly analyzing the chemistry of moon formation in distant planetary systems, the first to observe the molecular processes that create the building blocks of worlds separated from us by hundreds of light years. The universe we're discovering is far more chemically rich and dynamically complex than our ancestors could have imagined. Each new observation reveals processes and possibilities that expand our conception of what's achievable through natural cosmic evolution. The story of CT-CHAR-B represents just one chapter in an epic tale of world formation that's playing out simultaneously in countless systems throughout our galaxy. As you settle into the gentle rhythm of approaching sleep, carried along by the cosmic currents that connect all things in this vast universe, consider that the same fundamental processes we're observing around distant stars also operated in our own solar system billions of years ago. The moon that lights your nights, the planets that grace our sky, and the rich diversity of worlds throughout our cosmic neighborhood all emerged from similar chemistry and physics to what we're witnessing today in these distant moon factories. We are part of this ongoing story of cosmic evolution, temporary arrangements of matter and energy that have achieved the remarkable feat of consciousness and curiosity. In studying the formation of distant worlds, we're not just satisfying scientific curiosity, but participating in the universe's attempt to understand itself, to trace the pathways by which simple beginnings lead to complexity, beauty, and ultimately to minds capable of wonder at the magnificence of it all. The journey of discovery continues, with each new observation adding depth and richness to our understanding of how worlds come to be throughout this extraordinary cosmos we call home. The chemistry we're uncovering in CT Chabi's disk also reveals something profound about the interconnectedness of cosmic processes. When we trace the origins of the organic molecules detected around this distant world, we find that many of them share fundamental structural relationships. Acetylene can transform into benzene through cyclotrimerization reactions. Benzene can serve as a foundation for building even more complex polycyclic aromatic hydrocarbons. These aren't isolated chemical species floating independently through space, but members of interconnected molecular families that can transform into one another under the right conditions. This chemical connectivity suggests that circumplanetary disks operate as sophisticated reaction networks where molecular complexity can build systematically over time. Simple two-carbon molecules like acetylene provide the raw materials for constructing 6-carbon benzene rings. These rings can then link together to form larger aromatic structures, potentially creating molecules with dozens or even hundreds of carbon atoms. The progression from simple to complex occurs through well-understood chemical pathways, but observing it happening in a natural cosmic environment provides crucial validation of theoretical predictions. The presence of hydrogen cyanide adds another dimension to this chemical web. This deceptively simple molecule, containing just one carbon, one nitrogen, and one hydrogen atom, can participate in reactions that lead to some of the most important biological molecules known to science. Under appropriate conditions, hydrogen cyanide molecules can link together to form adenine, one of the 4 nucleotide bases that make up DNA. While the extreme environment around CT Chab makes biological processes impossible, the natural occurrence of hydrogen cyanide demonstrates that circumplanetary disks routinely produce molecules that are central to life as we understand it. The implications extend beyond simple molecular inventory to questions about how chemical information might be preserved and transmitted during moon formation. When dust grains and ice particles begin aggregating to form larger bodies, they carry with them the chemical signatures of their formation environment. Organic molecules incorporated during this early accretion phase could become trapped within moon interiors, creating chemical time capsules that preserve records of primordial circumplanetary chemistry for billions of years. These buried organic inventories might not remain dormant indefinitely. As moons evolve and develop internal heat sources through radioactive decay and tidal heating, the increased temperatures and pressures in their deep interiors could drive chemical reactions that gradually transform the original molecular inventory. Simple organic compounds might polymerize into more complex structures. Aromatic molecules could participate in condensation reactions that create even larger molecular networks. Over geological time, the chemistry inherited from circumplanetary disk formation could evolve into something far more sophisticated than what originally existed in the disk itself. The detection of carbon dioxide alongside the organic molecules in CT-CHARB's disk adds another layer of complexity to this chemical story. Carbon dioxide represents an oxidized form of carbon that contrasts with the reduced organic compounds like acetylene and benzene. The coexistence of both oxidized and reduced carbon species within the same environment suggests that the circumplanetary disk maintains chemical gradients that span a wide range of oxidation states. These redox gradients could have profound implications for the types of chemical processes that might occur on moons forming in such environments. Worlds that incorporate both organic compounds and oxidized carbon species during formation could develop internal chemistry that's far more dynamic than what we see in our own solar system. The interaction between reduced organic materials and oxidized compounds like carbon dioxide could drive chemical reactions that continue for millions or billions of years after moon formation is complete. Consider what might happen if substantial quantities of organic compounds and carbon dioxide become incorporated into a moon's interior during accretion. As the world undergoes thermal evolution and develops regions of elevated temperature and pressure, these chemical species could begin interacting in ways that create even more complex molecular systems. Organic molecules might undergo oxidation reactions that release energy while simultaneously creating new carbon compounds. Carbon dioxide could participate in reduction reactions that consume organic materials while producing methane, carbon monoxide, or other reduced carbon species. The energy released by such reactions could contribute to heating moon interiors and driving geological processes that wouldn't otherwise occur. Worlds with rich organic inventories might maintain active geology for much longer than purely inorganic satellites, creating dynamic environments where chemical evolution continues throughout their history. The surface expressions of this internal chemistry could include organic volcanism, hydrocarbon geysers, or atmospheric compositions dominated by complex carbon chemistry. The spatial distribution of molecules within CT-CHARB's circumplanetary disk also provides insights into how chemical gradients develop during the moon formation process. While we cannot directly resolve the disk structure, the spectroscopic data contains subtle signatures that reveal where different molecular species are concentrated within the circumplanetary environment. Temperature-sensitive molecules will be more abundant in regions where they can survive without thermal decomposition, while thermally stable species might be found throughout the disk. This chemical mapping suggests that moons forming at different distances from CT-CHARB could acquire dramatically different compositions, even though they all originate from the same circumplanetary disk. Inner satellites accreting close to the planet might incorporate primarily refractory organic compounds that can survive in high-temperature environments. These could include graphitic carbon, polycyclic aromatic hydrocarbons, and other thermally stable organic materials that would give the resulting moons distinctive properties. Middle-distance moons might sample a broader range of chemical species as they accrete material from transition zones where both volatile and refractory compounds can coexist. These worlds could develop layered internal structures reflecting the varied chemistry available during their formation. The outer portions might be dominated by volatile organic compounds and ices, while deeper layers contain more refractory materials that were incorporated early in the accretion process. Outer moons forming in the coldest regions of the circumplanetary disk could acquire compositions dominated by volatile organic compounds that would be destroyed in warmer environments closer to the planet. These satellites might resemble enormous versions of cometary nuclei, with surfaces rich in complex organic materials preserved in deep frozen states. If such worlds later migrated to warmer orbital positions or developed internal heat sources, the sublimation and chemical processing of these organic inventories could create spectacular atmospheric displays and surface changes. The long-term evolution of chemically diverse moon systems opens up possibilities that stretch our understanding of how satellite systems might develop over cosmic time. Gravitational interactions between multiple moons could cause orbital migrations that bring satellites formed in different chemical environments into close proximity. When this happens, collisional processes might exchange material between worlds with dramatically different compositions, creating hybrid objects that combine chemical inventories from multiple formation zones. Some moons might capture debris from the circumplanetary disk long after their initial formation, gradually accreting additional layers of material with different chemical signatures. Others might lose portions of their original inventory through impact processes, atmospheric escape, or gravitational interactions, creating a complex history of chemical gain and loss that unfolds over billions of years. The gravitational stirring caused by multiple moons in resonant orbital configurations could also influence the evolution of their internal chemistry. Tidal heating generated by gravitational interactions might create temperature and pressure conditions that drive chemical reactions impossible in more quiescent environments. The resulting internal differentiation could separate different chemical species into distinct layers, creating worlds with complex internal architectures that reflect both their formation chemistry and subsequent evolutionary processes. Webb's successful analysis of CT-CHAR-B's circumplanetary chemistry also demonstrates the potential for studying even more distant and exotic moon-forming environments. The techniques developed for this groundbreaking observation can now be applied to planetary systems throughout our galactic neighborhood, each potentially revealing different aspects of circumplanetary chemistry and moon formation physics. Some future targets might include planets orbiting different types of stars, where varying stellar radiation environments could drive chemical processes unlike anything we see around CT-CHAR-B young. Massive stars produce intense ultraviolet radiation that could create circumplanetary chemistry, dominated by photochemical reactions. Lower mass stars with different spectral characteristics might favor entirely different molecular synthesis pathways. Binary star systems could subject circumplanetary disks to complex radiation fields and gravitational perturbations that produce unique chemical signatures. The diversity of planetary masses and orbital configurations accessible to Webb observations also promises to reveal how these factors influence circumplanetary chemistry. More massive planets might maintain hotter circumplanetary disks that favor different types of chemical reactions. Planets on highly elliptical orbits could experience varying stellar irradiation that drives seasonal chemical cycles within their circumplanetary environments. Planets in multiple planet systems might have their circumplanetary chemistry influenced by gravitational perturbations from neighboring worlds. Each new system studied will add another piece to the puzzle of understanding how common the complex chemistry observed around CT-CHAR-B might be throughout the galaxy. We might discover that organic-rich circumplanetary disks are the norm rather than the exception, suggesting that chemically sophisticated moons are abundant throughout the universe. Alternatively, we might find that CT-CHAR-B represents an unusual case, with most circumplanetary environments exhibiting simpler chemistry dominated by water, carbon monoxide, and other basic molecules. The statistical understanding that will emerge from these surveys has profound implications for astrobiology and our search for life beyond the solar system. If complex circumplanetary chemistry proves to be common, then the universe might be populated with countless moons that acquired sophisticated molecular inventories during formation. These chemical foundations could provide starting points for continued evolution over billions of years, potentially creating environments where biological processes could emerge and flourish. The concept of habitable moons has gained increasing attention as we've come to recognize that satellites might actually represent the most common, potentially life-bearing worlds in the universe. Unlike planets, which must orbit within narrow habitable zones around their host stars to maintain liquid water on their surfaces, moons can maintain subsurface oceans through tidal heating, regardless of their distance from the central star. This dramatically expands the volume of space where habitable conditions might exist. If these tidally heated moons also inherit complex organic chemistry from their formation environments, they could represent extraordinarily promising targets for astrobiological investigation. The combination of liquid water, organic compounds, and long-term stability could create conditions ideal for the emergence of life. The chemical diversity suggested by circumplanetary disk observations raises the possibility that any life emerging on such worlds might be based on biochemistries quite different from what we see on Earth. Carbon-rich moons forming in environments similar to CT-CHARB's disk might support organisms that utilize abundant hydrocarbon chemistry for their metabolic processes. These life forms might derive energy from organic synthesis reactions, incorporate aromatic compounds into their structural biochemistry, or even develop entirely novel approaches to organizing complex chemistry that we haven't yet imagined. The natural occurrence of molecules like benzene and hydrogen cyanide in circumplanetary environments suggests that the chemical foundations for alternative biochemistries might be established during moon formation itself. The temporal aspects of circumplanetary chemical evolution also provide important insights into the timescales available for developing biological complexity. The rapid chemical evolution observed in CT-CHARB's system, where sophisticated organic chemistry developed in just 2 million years, demonstrates that complex molecular systems can emerge with remarkable speed on cosmic timescales. This suggests that the transition from geochemistry to biochemistry might occur more readily than previously thought, particularly in environments where rich organic inventories are available from the beginning. The ongoing chemical processing that likely continues within circumplanetary disks throughout the moon formation period could also provide multiple opportunities for increasing molecular complexity. Rather than representing a single snapshot of chemical conditions, these environments probably undergo continuous evolution as physical conditions change, new material flows in from the outer disk, and chemical reactions proceed under varying temperature and pressure regimes. This dynamic evolution means that moons forming at different times during the circumplanetary disk's lifetime might acquire quite different chemical signatures. Early forming satellites might incorporate relatively simple organic compounds that were present during the initial phases of chemical evolution. Later forming moons could inherit more sophisticated molecular inventories that developed as the circumplanetary chemistry matured. The most complex chemistry might be preserved in the final generations of moons that form just before the disk dissipates completely. The preservation of these chemical time signatures within moon populations could provide future astronomers with detailed records of how circumplanetary chemistry evolved throughout the formation period. By analyzing the compositions of different satellites within the same system, we might be able to reconstruct the complete history of chemical development from the simple starting materials present when the circumplanetary disk first formed to the sophisticated molecular inventories that existed during the final phases of moon formation. Such detailed chemical archaeology would provide unprecedented insights into the fundamental processes that govern the emergence of complexity in cosmic environments. We would be able to trace the specific pathways by which simple molecules transform into complex organic systems, understand the physical conditions that favor different types of chemical evolution, and predict what types of molecular inventories might be expected in circumplanetary disks under various formation scenarios. The success of Webb's circumplanetary disk observations also highlights the remarkable progress that's been made in infrared astronomy over the past few decades. The technical challenges overcome in isolating CT-CHAR-B's chemical signatures from overwhelming stellar contamination represent achievements at the very limits of what's possible with current technology. The fact that we can now routinely conduct such observations opens entirely new avenues for understanding planetary system formation and evolution. Future infrared telescopes with even greater sensitivity and spatial resolution will undoubtedly reveal aspects of circumplanetary chemistry that remain hidden with current capabilities. We might eventually be able to spatially resolve the chemical gradients within individual circumplanetary disks, directly observing how molecular inventories vary with distance from the central planet. Such observations would provide crucial tests of theoretical models for circumplanetary chemistry and physics. The development of new spectroscopic techniques optimized for studying faint circumplanetary emission could also reveal molecular species that are currently below our detection thresholds. The inventory of organic compounds detected around CT-CHAR-B likely represents only the most abundant species present in the disk. Smaller concentrations of even more complex molecules might exist, but remain undetectable with current methods. Future observations might reveal circumplanetary chemistry of such sophistication that it challenges our understanding of what's possible through natural chemical processes. The combination of improved observational capabilities and advancing theoretical understanding promises to transform our comprehension of moon formation over the coming decades. We're entering an era where the birth of satellite systems can be studied in exquisite detail, where the chemical processes that determine moon compositions can be observed directly, and where the diversity of circumplanetary environments throughout the galaxy can be systematically surveyed and characterized. This observational revolution will undoubtedly reveal surprises that we haven't yet anticipated. The complexity and beauty of CT-CHAR-B's circumplanetary chemistry already exceed what many theoretical models predicted, suggesting that nature's capacity for creating sophisticated molecular systems is even greater than we imagined. Each new system we study will likely present unique chemical signatures and evolutionary pathways that expand our understanding of what's possible in these remarkable cosmic environments. The implications extend beyond pure scientific curiosity to fundamental questions about our place in the universe and the prevalence of complex chemistry throughout the cosmos. If circumplanetary disks routinely develop the kind of sophisticated molecular inventories observed around CT-CHAR-B, then the universe might be far more chemically rich and dynamically active than we've previously recognized. This chemical richness could have profound implications for understanding the emergence of complexity at all scales throughout the universe. From the formation of complex molecules in circumplanetary disks to the development of intricate geological processes on the worlds that form from disk material, we're witnessing a cosmos that exhibits remarkable creativity in organizing matter and energy into increasingly sophisticated structures and systems. The story of CT-CHAR-B represents just the beginning of our exploration into these distant laboratories of chemical evolution. As we continue to study circumplanetary environments throughout our galactic neighborhood, we're building a comprehensive picture of how nature creates the chemical foundations for worlds unlike anything in our own solar system. Each observation adds new chapters to an epic tale of cosmic chemistry that connects the formation of simple molecules in stellar nurseries to the emergence of complex worlds capable of harboring life itself. Tonight, as you drift towards sleep under a sky filled with countless stars, each potentially surrounded by their own families of worlds in various stages of formation and evolution, consider that we're living through one of the most extraordinary periods in the history of human discovery. We're the first generation capable of directly observing the chemical processes that create the building blocks of distant worlds. The first to analyze molecular inventories in planetary systems separated from us by hundreds of light years. The universe we're uncovering through these observations is far more dynamic and chemically sophisticated than our ancestors could have dreamed. Every new discovery reveals processes and possibilities that expand our understanding of how complexity emerges from simplicity, how chemistry gives rise to worlds, and how the fundamental forces of nature conspire to create environments of breathtaking beauty and diversity. The gentle light of our own moon, filtering through your window as you prepare for sleep, carries within it the story of our own satellite's formation billions of years ago in a circumplanetary disk that might have been remarkably similar to what we're observing around CT B today. The same chemical processes, the same physical forces, the same natural creativity that we're witnessing in distant star systems also operated in our own cosmic neighborhood when the solar system was young. We are part of this ongoing story of cosmic evolution, temporary arrangements of stardust that have achieved the remarkable feat of consciousness and curiosity. In studying the formation of distant moons, we're participating in the universe's attempt to understand itself, tracing the pathways by which simple beginnings lead to complexity, beauty, and ultimately to minds capable of wonder at the magnificence of creation itself. As you settle into the rhythm of approaching sleep, carried along by the same fundamental forces that govern the dance of molecules in distant circumplanetary disks, remember that every breath you take, every heartbeat that sustains you, every thought that crosses your mind is part of the same cosmic story that's unfolding around CT B and countless other worlds throughout our galaxy. The chemistry of life itself, the organic molecules that make consciousness possible, the complex networks of carbon, hydrogen, oxygen, and nitrogen that constitute your very being, all trace their origins to stellar nucleosynthesis and cosmic chemical processes, not unlike those we're observing in these distant moon factories. You are made of star stuff that has learned to contemplate stars, cosmic chemistry that has achieved the ability to study cosmic chemistry. The discovery of complex organic molecules in B's circumplanetary disk reminds us that the universe is filled with the potential for chemistry, complexity, and perhaps even consciousness to emerge wherever conditions allow. We may not be alone in our capacity for wonder and discovery. Somewhere among the countless worlds that are forming around distant stars, other arrangements of cosmic matter might be achieving their own forms of awareness, conducting their own investigations into the nature of reality. The interconnectedness revealed by these observations, the way simple molecules transform into complex chemical networks, the manner in which individual worlds participate in larger cosmic processes, all reflect the fundamental unity that underlies the apparent diversity of the universe. Every moon forming around B, every molecule detected in its circumplanetary disk, every photon of infrared light that carries chemical signatures across hundreds of light years of space, is part of the same magnificent tapestry of existence that includes our own world and our own consciousness. Tonight, as cosmic processes continue their ancient work of creating new worlds in distant systems, As molecules dance and combine in circumplanetary disks we're only beginning to explore, as the universe continues its patient work of organizing matter and energy into ever more sophisticated forms, you can rest in the knowledge that you're part of something far grander and more beautiful than any single world or system could contain. The story continues to unfold, with each new observation revealing additional layers of complexity and wonder in the cosmic environments where new worlds are born. We stand at the threshold of discoveries that will reshape our understanding of planetary formation, chemical evolution, and the prevalence of complex chemistry throughout the universe. The journey of exploration that brought us to CT-CHARB's remarkable circumplanetary disk is just beginning, with countless more systems waiting to share their secrets and expand our appreciation for the incredible creativity embedded in the fundamental laws of nature. In this moment of quiet contemplation, as you prepare to join the cosmic rhythm of sleep and dreams, you participate in the same universal processes that govern the formation of moons around distant worlds. The chemistry of consciousness that allows you to ponder these cosmic mysteries, the molecular networks that generate thoughts and dreams, the organic complexity that makes wonder possible, all emerged from the same stellar alchemy and circumplanetary chemistry that we're now observing in action around CT-CHARB and other distant worlds. The universe dreams through us, contemplates itself through our consciousness, and continues its magnificent work of creation through every breath we take and every question we dare to ask about the nature of existence itself. The molecular dance occurring within CT-CHARB's circumplanetary disk reveals something extraordinary about the universe's capacity for creating chemical complexity from seemingly simple beginnings. When astronomers first detected the spectral signatures of benzene and acetylene in this distant environment, they weren't just identifying individual molecules floating in space. They were witnessing the emergence of interconnected chemical networks that could serve as foundations for worlds unlike anything we've ever imagined. Picture the circumplanetary disk as a vast cosmic laboratory where chemistry operates under conditions that stretch the boundaries of what we consider possible. Temperatures fluctuate across orders of magnitude, from the scorching inner regions close to the massive planet to the frigid outer zones where volatile compounds can survive intact. Pressures vary dramatically as gravitational forces compress some regions while others remain tenuous and diffuse. Radiation fields created by the young central star drive photochemical reactions that break molecular bonds and forge new ones in endless cycles of destruction and creation. Within this dynamic environment, simple two-carbon molecules like acetylene encounter conditions that promote their transformation into more complex structures. 3 acetylene molecules can combine through cyclotrimerization reactions to form benzene rings, creating the fundamental building blocks for even larger aromatic compounds. These benzene rings can then link together in various configurations, potentially generating polycyclic aromatic hydrocarbons with dozens or hundreds of carbon atoms arranged in intricate molecular architectures. The presence of hydrogen cyanide adds another dimension to this chemical complexity. This deceptively simple molecule, containing just 1 carbon, 1 nitrogen, and 1 hydrogen atom, can participate in polymerization reactions that create some of the most biologically significant compounds known to science. Under appropriate conditions, hydrogen cyanide molecules can chain together to form adenine, one of the 4 nucleotide bases that comprise DNA. While the extreme environment around CT-CHAB makes biological processes impossible, the natural occurrence of hydrogen cyanide demonstrates that circumplanetary disks routinely produce molecules that are central to life as we understand it. The coexistence of both oxidized and reduced carbon species within the same circumplanetary environment creates chemical gradients that span a remarkable range of oxidation states. Carbon dioxide represents the fully oxidized form of carbon, while molecules like acetylene and benzene exist in highly reduced states. This chemical diversity suggests that moons forming in different regions of the disk could acquire dramatically different compositions depending on which chemical species dominate their local formation environment. Consider what might happen to a world that incorporates both organic compounds and carbon dioxide during its accretion process. As this hypothetical moon undergoes thermal evolution over millions of years, the interaction between reduced organic materials and oxidized carbon species could drive chemical reactions that continue long after the original circumplanetary disk has dissipated. Organic molecules might undergo oxidation reactions that release energy while creating new carbon compounds. Carbon dioxide could participate in reduction processes that consume organic materials while producing methane, carbon monoxide, or other reduced carbon species. The energy released by such reactions could contribute to heating the moon's interior and driving geological processes that wouldn't occur in purely inorganic worlds. Satellites with rich organic inventories might maintain active geology for much longer periods than conventional rocky or icy moons, creating dynamic environments where chemical evolution continues throughout their entire history. The surface expressions of this internal chemistry could include phenomena we've never observed in our own solar system: organic volcanism that erupts complex hydrocarbon compounds, geysers that spray organic molecules into space, or atmospheric compositions dominated by sophisticated carbon chemistry. The spatial distribution of molecules within CT-CHAR-B's circumplanetary disk also provides crucial insights into how chemical gradients develop during moon formation. While current observations cannot directly resolve the disk's structure, the spectroscopic data contains subtle signatures that reveal where different molecular species concentrate within the circumplanetary environment. Temperature-sensitive compounds will be more abundant in regions where they can survive without thermal decomposition, while thermally stable species might exist throughout the entire disk. This chemical stratification means that moons forming at different orbital distances could develop remarkably diverse compositions, even though they all originate from the same parent disk. Inner satellites accreting close to the massive planet might incorporate primarily refractory organic compounds capable of surviving high-temperature environments. These could include graphitic carbon, thermally stable aromatic molecules, and other heat-resistant materials that would give the resulting moons distinctive properties unlike anything in our solar system. Moons forming at intermediate distances might sample broader ranges of chemical species as they accrete material from transition zones where both volatile and refractory compounds coexist. These worlds could develop complex layered internal structures, reflecting the varied chemistry available during their formation process. Outer portions might be dominated by volatile organic compounds and various ices, while deeper layers contain more refractory materials incorporated early in the accretion sequence. Satellites forming in the outermost regions of the circumplanetary disk could acquire compositions dominated by volatile organic compounds that would be destroyed in warmer environments closer to the planet. These worlds might resemble enormous versions of cometary nuclei, with surfaces rich in complex organic materials preserved in deep frozen states for billions of years. If such moons later migrated to warmer orbital positions or developed internal heat sources through radioactive decay or tidal interactions, the sublimation and chemical processing of these organic inventories could create spectacular atmospheric displays and dramatic surface transformations. The long-term evolution of chemically diverse moon systems opens possibilities that challenge our understanding of how satellite systems might develop over cosmic time. Gravitational interactions between multiple moons could cause orbital migrations that bring satellites formed in different chemical environments into close proximity. When this occurs, collisional processes might exchange material between worlds with dramatically different compositions, creating hybrid objects that combine chemical inventories from multiple formation zones within the original circumplanetary disk. Some moons might continue accreting debris from the circumplanetary disk long after their initial formation, gradually building additional layers of material with different chemical signatures. Others might lose portions of their original inventory through impact processes, atmospheric escape, or gravitational interactions with their parent planet, creating complex histories of chemical gain and loss that unfold over billions of years of evolution. The gravitational stirring caused by multiple moons in resonant orbital configurations could also profoundly influence the evolution of their internal chemistry. Tidal heating generated by gravitational interactions might create temperature and pressure conditions that drive chemical reactions impossible in more quiescent environments. The resulting internal differentiation could separate different chemical species into distinct compositional layers, creating worlds with intricate internal architectures that reflect both their original formation chemistry and subsequent evolutionary processes. Webb's successful analysis of CT-Charby's circumplanetary chemistry demonstrates the potential for studying even more distant and exotic moon-forming environments throughout our galactic neighborhood. The sophisticated techniques developed for this groundbreaking observation can now be applied to planetary systems around different types of stars, each potentially revealing unique aspects of circumplanetary chemistry and moon formation physics under varying stellar conditions. Future observations might target planets orbiting young massive stars that produce intense ultraviolet radiation capable of driving photochemical reactions processes unlike anything occurring around CT-Charby. The high-energy stellar photons could create circumplanetary chemistry dominated by exotic molecular species that form only under extreme radiation conditions. Alternatively, planets around lower mass stars with different spectral characteristics might favor entirely different molecular synthesis pathways, potentially producing circumplanetary disks with chemical inventories we haven't yet learned to recognize or interpret. Binary star systems present particularly intriguing targets for future circumplanetary observations. Planets in such systems could experience complex radiation environments as they orbit around both stellar components or maintain orbits around individual stars within the binary. The varying stellar irradiation patterns could drive seasonal chemical cycles within circumplanetary disks, creating temporal variations in molecular abundances and reaction rates that produce chemical signatures unlike anything seen in single-star systems. The diversity of planetary masses and orbital configurations accessible to Webb's observational capabilities also promises to reveal how these fundamental parameters influence circumplanetary chemistry. More massive planets might maintain hotter circumplanetary disks that favor different types of chemical reactions and molecular synthesis pathways. The increased gravitational binding energy could also extend the lifetime of circumplanetary disks, providing more time for complex chemistry to develop before the disk material is either accreted by forming moons or dispersed into interplanetary space. Planets on highly elliptical orbits could experience dramatic variations in stellar irradiation as they move between closest and farthest approach to their host stars. These orbital variations might drive cyclical changes in circumplanetary chemistry, with different molecular species dominating during different phases of the orbital period. The resulting chemical complexity could exceed anything observed in systems where planets maintain more circular orbits and experience relatively constant stellar heating. Planets in multiple planet systems might have their circumplanetary chemistry influenced by gravitational perturbations and dynamical interactions with neighboring worlds. Close planetary encounters could disrupt circumplanetary disks and trigger chemical processes through shock heating and compression. Resonant interactions between planets could create periodic perturbations that drive mixing and transport within circumplanetary environments, potentially homogenizing chemical gradients that would otherwise remain stratified. Each new system studied will contribute another piece to the growing puzzle of understanding how common the complex chemistry observed around CTCHB might be throughout the galaxy. Statistical analysis of multiple circumplanetary disk observations will eventually allow astronomers to determine whether organic-rich chemistry represents the norm or an exceptional case among moon-forming environments. The implications for astrobiology become increasingly compelling as we consider the possibility that complex circumplanetary chemistry might be widespread throughout the universe. If sophisticated organic molecular inventories prove common in these environments, then countless moons throughout the galaxy could have acquired the chemical foundations necessary for supporting life during their formation processes. The concept of habitable moons has gained significant attention from astrobiologists as we've recognized that satellites might actually outnumber planets as potentially life-bearing worlds. Unlike planets, which must orbit within relatively narrow habitable zones around their host stars to maintain liquid water on their surfaces, moons can sustain subsurface oceans through tidal heating mechanisms that operate regardless of their distance from the central star. This dramatically expands the volume of space where habitable conditions might exist throughout the galaxy. If tidally heated moons also inherit complex organic chemistry from their circumplanetary formation environments, they could represent extraordinarily promising targets for astrobiological investigation. The combination of liquid water, sophisticated organic compounds, and long-term environmental stability could create ideal conditions for the emergence and evolution of life. The chemical diversity suggested by circumplanetary disk observations raises fascinating possibilities that any life emerging on such worlds might be based on biochemistries quite different from terrestrial biology. Carbon-rich moons forming in environments similar to CTCHB's disk might support organisms that utilize abundant hydrocarbon chemistry for their metabolic processes. These hypothetical life forms might derive energy from organic synthesis reactions, incorporate aromatic ring structures into their biochemical machinery, or develop entirely novel approaches to organizing complex chemistry that we haven't yet imagined. The natural occurrence of molecules like benzene and hydrogen cyanide in circumplanetary environments suggests that the chemical foundations for alternative biochemistries might be established during the moon formation process itself. The rapid chemical evolution observed in CTCHB's system, where sophisticated organic chemistry developed in just 2 million years, demonstrates that complex molecular systems can emerge with remarkable speed on cosmic timescales. This temporal efficiency suggests that the transition from simple geochemistry to the complex chemical networks that might support biological processes could occur more readily than previously thought, particularly in environments where rich organic inventories are available from the very beginning of world formation. The ongoing chemical processing that likely continues within circumplanetary disks throughout the moon formation period provides multiple opportunities for increasing molecular complexity over time, rather than representing static repositories of chemical materials. These environments probably undergo continuous evolution as physical conditions change. New material flows inward from outer disk regions, and chemical reactions proceed under varying temperature, pressure, and radiation regimes. This dynamic chemical evolution means that moons forming at different times during a circumplanetary disk's lifetime might acquire quite different chemical signatures, reflecting the maturity of the chemical processes operating when they accreted. Early forming satellites might incorporate relatively simple organic compounds present during initial phases of chemical evolution, while later forming moons could inherit more sophisticated molecular inventories that developed as circumplanetary chemistry matured over time. The most complex chemistry might be preserved in the final generations of moons that form just before circumplanetary disks dissipate completely. These late-forming satellites could represent chemical time capsules that preserve the most advanced stages of circumplanetary molecular evolution, potentially harboring organic inventories of unprecedented complexity and sophistication. The preservation of these chemical time signatures within moon populations could provide future astronomers with detailed records of how circumplanetary chemistry evolved throughout entire formation periods. By analyzing the compositions of different satellites within the same system, researchers might be able to reconstruct complete histories of chemical development from simple starting materials present when circumplanetary disks first formed to the sophisticated molecular inventories that existed during final phases of moon formation. Such detailed chemical archaeology would provide unprecedented insights into fundamental processes governing the emergence of complexity in cosmic environments. Scientists would be able to trace specific pathways by which simple molecules transform into complex organic systems, understand physical conditions that favor different types of chemical evolution, and predict what molecular inventories might be expected in circumplanetary disks under various formation scenarios throughout the galaxy. The technical achievements represented by Webb's circumplanetary disk observations highlight remarkable progress in infrared astronomy over recent decades. The challenges overcome in isolating CT-CHAR-B's faint chemical signatures from overwhelming stellar contamination represent accomplishments at the very limits of current technological capabilities. The fact that such observations can now be conducted routinely opens entirely new avenues for understanding planetary system formation and evolution throughout cosmic history. Future infrared telescopes with even greater sensitivity and spatial resolution will undoubtedly reveal aspects of circumplanetary chemistry that remain hidden with current observational capabilities. Astronomers might eventually achieve spatial resolution sufficient to directly observe chemical gradients within individual circumplanetary disks, watching how molecular inventories vary with distance from central planets and change over time as formation processes proceed. The development of new spectroscopic techniques optimized specifically for studying faint circumplanetary emission could reveal molecular species that currently exist below detection thresholds. The inventory of organic compounds detected around CT-CHAR-B likely represents only the most abundant chemical species present in the disk. Smaller concentrations of even more complex molecules might exist, but remain undetectable with present methods and instrumentation. Future observations might reveal circumplanetary chemistry of such sophistication that it challenges our understanding of what's possible through natural chemical processes operating in cosmic environments. The complexity and beauty already discovered in CT-CHAR-B's circumplanetary disk exceed what many theoretical models predicted, suggesting that nature's capacity for creating sophisticated molecular systems surpasses even our most optimistic expectations. The combination of improved observational capabilities and advancing theoretical understanding promises to revolutionize comprehension of moon formation over the coming decades. We're entering an era where satellite system birth can be studied in exquisite detail, where chemical processes determining moon compositions can be observed directly, and where the diversity of circumplanetary environments throughout the galaxy can be systematically surveyed and characterized with unprecedented precision. This observational revolution will undoubtedly reveal surprises that haven't yet been anticipated by current theoretical frameworks. Each new system studied will likely present unique chemical signatures and evolutionary pathways that expand our understanding of what's possible in these remarkable cosmic laboratories, where worlds are born from the fundamental forces of chemistry and physics. The implications extend far beyond pure scientific curiosity to fundamental questions about our place in the universe and the prevalence of complex chemistry throughout the cosmos. If circumplanetary disks routinely develop sophisticated molecular inventories, similar to what we observe around CT-Char b, then the universe might be far more chemically rich and dynamically active than we've previously recognized or imagined possible. This chemical richness could have profound implications for understanding the emergence of complexity at all scales throughout the universe. From the formation of intricate molecules in circumplanetary disks to the development of sophisticated geological processes on the worlds that eventually form from disk material, we're witnessing a cosmos that exhibits remarkable creativity in organizing matter and energy into increasingly complex structures and systems. The story of CT-Char b represents merely the opening chapter of our exploration into these distant laboratories of chemical evolution. As we continue studying circumplanetary environments throughout our galactic neighborhood, we're building a comprehensive picture of how nature creates the chemical foundations for worlds, unlike anything in our own solar system. Each new observation adds depth and richness to an epic tale of cosmic chemistry that connects the formation of simple molecules in stellar nurseries to the emergence of complex worlds potentially capable of harboring life itself. Tonight, as you drift towards sleep beneath a sky filled with countless stars, each potentially surrounded by families of worlds in various stages of formation and evolution, consider that we're living through one of the most extraordinary periods in the history of human discovery. We represent the first generation capable of directly observing chemical processes that create the building blocks of distant worlds, the first to analyze molecular inventories in planetary systems separated from us by hundreds of light years of space and time. The universe we're uncovering through these observations reveals itself to be far more dynamic and chemically sophisticated than our ancestors could have conceived. Every new discovery unveils processes and possibilities that expand our understanding of how complexity emerges from simplicity, how chemistry gives rise to worlds, and how fundamental forces of nature conspire to create environments of breathtaking beauty and diversity throughout the cosmic web. The gentle glow of our own moon, perhaps visible through your window as you prepare for sleep, carries within its ancient light the story of our satellite's formation billions of years ago in a circumplanetary disk that might have been remarkably similar to what we're observing around CT-Char b today. The same chemical processes, the same physical forces, the same natural creativity that we're witnessing in distant star systems also operated in our own cosmic neighborhood when the solar system was young and the dance of world formation was just beginning. We are integral parts of this ongoing story of cosmic evolution, temporary arrangements of stardust that have achieved the remarkable feat of consciousness and curiosity about our own origins. In studying the formation of distant moons, we participate in the universe's attempt to understand itself, tracing the pathways by which simple beginnings lead to complexity, beauty, and ultimately to minds capable of wonder at the magnificence of creation unfolding around us. As you settle into the rhythm of approaching sleep, carried along by the same fundamental forces that govern molecular dances in distant circumplanetary disks, remember that every breath sustaining you, every heartbeat maintaining your existence, every thought crossing your consciousness is part of the same cosmic story that's unfolding around CT-Char b and countless other worlds throughout our galaxy and beyond. The chemistry of consciousness itself, the organic molecules that make awareness possible, the complex networks of carbon, hydrogen, oxygen, and nitrogen that constitute your very being, all trace their ultimate origins to stellar nucleosynthesis and cosmic chemical processes, not unlike those we're observing in these distant factories, where new moons are born from the raw materials of creation itself. You are made of star stuff that has learned to contemplate stars, cosmic chemistry that has achieved the ability to study cosmic chemistry across the vast reaches of space and time. The discovery of complex organic molecules in CT-CHAR-B's circumplanetary disk reminds us that the universe overflows with potential for chemistry, complexity, and perhaps even consciousness to emerge wherever conditions align in just the right way. We may not be alone in our capacity for wonder and discovery. Somewhere among the countless worlds forming around distant stars throughout our galaxy, other arrangements of cosmic matter might be achieving their own forms of awareness, conducting their own investigations into the nature of reality, asking their own questions about the origins of their existence. The interconnectedness revealed by these observations, the way simple molecules transform into complex chemical networks, the manner in which individual worlds participate in larger cosmic processes, all reflect the fundamental unity that underlies the apparent diversity of the universe. Every moon forming around CT-CHAR-B, every molecule detected in its circumplanetary disk, every photon of infrared light that carries chemical signatures across hundreds of light-years of space, participates in the same magnificent tapestry of existence that includes our own world and our own consciousness. The research team's dedication to extracting meaning from Webb's data reveals something beautiful about the human spirit of inquiry. Spending an entire year sifting through spectroscopic signatures, developing new analytical techniques, and pushing the boundaries of what's possible with current technology, all to understand the chemistry light began traveling toward us during of a world so distant that it's the height of medieval civilization here on Earth. This perseverance speaks to something profound about our relationship with the cosmos. We are not content to simply exist within the universe. We feel compelled to understand it, to trace the connections between distant worlds and our own existence, to find meaning in the vast web of processes that connect the smallest molecules to the largest structures in the cosmic hierarchy. The story unfolding around CT-CHAR-B continues to evolve as astronomers analyze additional aspects of Webb's unprecedented dataset. Each molecular signature decoded, each chemical pathway identified, each physical process understood, brings us closer to comprehending our own cosmic origins and our place in the vast community of worlds that populate the universe. The discovery of CT-CHAR-B's carbon-rich moon factory represents far more than a single astronomical observation. It's a window into the fundamental processes that shape worlds throughout our galaxy, revealing that the universe's capacity for creating complex chemistry and diverse satellite systems exceeds our wildest imagination. As you drift into sleep tonight, remember that we're living through the first moments of a new era in cosmic exploration, where the birth of distant moons can be witnessed in real time, and the chemical foundations of countless worlds await our discovery. Sweet dreams, fellow cosmic explorers. The universe continues its magnificent work of creation, and we are privileged to witness its unfolding story.